Okay, so today's lesson is going to go through how to do the worksheet that I already gave you, which is those molar volume calculations for gases. So this is a little bit different. So I think we went through these notes, at least I hope we did. I know I did in one of the sections, so if you don't have these, please get them. I think I went through this and then through this. But remember so I talked about Avogadro's hypothesis and how that Avogadro, we always think of Avogadro's number, that 6.02 times 10 to the 23rd when we're talking about particles. However, when that Avogadro, really, he didn't come up with that number, but what he did come up with was this idea that equal volumes of gases, if they're at the same temperature and pressure, will contain equal numbers of particles, regardless of which gas we're talking about. It doesn't matter. They're all kind of the same. And we know that the number of particles of 1 mole, which remember moles are how many, or eaches, if you will. If we have 1 mole of particles of a gas at standard temperature and pressure, it will occupy 22.4 liters of volume. So that's the volume. And I kind of drew just a super cool diagram. I'm sure that everybody's impressed with this. But this is hydrogen. Oh, and then I did go back and say, okay, really hydrogen is, right, it's diatomic. So it would be hydrogen bonded with another hydrogen. So these are really diatomic molecules of hydrogen, where this is single atoms of argon and so on. Argon is much heavier than hydrogen, but still, because gases are mostly empty space, we know that it will have the same number of particles of the gas. So if you didn't get that, I'll post the notes so that you can go back and get that. So we can use this awesome little number as a conversion factor, right? 1 mole of a gas, so this is only true for gases. 1 mole of a gas at standard temperature and pressure will occupy 22.4 liters. Or if I have 22.4 liters of gas at standard temperature and pressure, I will have 1 mole of particles of the gas. So let's do a couple of little mathy problems with that. So let's just work through this. And again, I think maybe I went through this with first hour, but not with my second hour. So how many moles of water vapor are in a 50.5 liter sample? So let's look at our path. And actually, I'm going to jump ahead to this. So this is kind of that diagram. So far, we had only talked about going from mass to moles, or moles to mass, or from mass all the way to particles, or particles to moles. So we've only done this bottom part here, but now we've introduced a whole new highway that goes all the way up to moles, or that volume of a gas from moles. So you'll see the arrow goes in either direction. So we can go from moles to volume or volume to moles, and all we have to do is remember this simple little conversion factor. So let's go back and do this example. How many moles of water vapor are in 50.5 liter sample of water? I have to understand that I'm starting with liters, and I want to get to moles. Okay, this is water vapor, so it's a gas. Liters, so if I look at my conversion factor here, remember whatever you start with, your first conversion factor has to be, how am I going to get rid of that, right? Which means that liters has to go on the bottom. So I have liters on the bottom. So what has to go on top? Well, I only have these two conversion factors, so obviously it's going to be 22.4 liters on the bottom, and 1 mole on top. Sorry, writing with my mouse. Not the best at it, working on it. So 1 mole goes on top. When I put this in my calculator, I do have to remember this is like a whole number over 1. So 50.5 times 1 divided by 22.4, 2.25 moles of water vapor. So that's the way we solve that. Let's do some that are maybe a little bit more complicated. Let me go to here. Da, 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 da. Let's say, let me get rid of this. Let's say maybe I want to go, let's do a 2-step problem. Because we're cool like that. We're ready for 2-step problems. Hitting the big time. Getting all of our conversion factors in here. Let's look at, I'm going to pause this and write something super cool. All right, so here's something interesting. If I have the problem, if I want to figure out how many particles are in, and actually I'm going to change this to how many molecules, because that seems more along the lines of what we talk about. How many molecules of a gas are in 35 liters? You will notice I didn't tell you what gas it was. But here's the brilliant part of this, because this doesn't involve finding any molar mass or anything like that. It doesn't matter what gas, right? You can see it's the same conversion factor that goes from volume of a gas to moles. For any gas, it doesn't matter. And then, of course, from moles to particles, again, doesn't matter. So this is pretty simple to set up. My path is going to be, let me do this in blue, is going to go from liters, which is the volume, right? Volume is in liters, please know that. That's a terrible L. I'm going from liters, I'm going to go to moles, and then, gosh, can you hear my lizard is going crazy? And then to molecules, which of course is our particles down here. So molecules. So my path is from here to here. So here's how we would set that up. 35 liters. I know I'm really far from the microphone. So here's how a couple of words to the wise, and we talk about this every time. Know how to use your calculator. We're going to have to put this in parentheses. So I started with liters. My first step is to get rid of liters. So that's my first conversion factor. Everything, my magic moles, everything has to go through moles every time. So first of all, I'm getting 2 moles. And then I'm converting from moles to particles. Boom, there you have it. So 9.4 times 10 to the 23rd molecules of a gas. And again, it doesn't matter which gas, they're all going to be the same because this is the molar volume of any gas. And obviously we could go from grams to moles to particles of a gas. We would have to know which gas because then we need that molar mass piece. If we were going backwards, we would simply flip these, right? We would start with molecules and work backwards, and then, right, moles would be on top, and right, so we can kind of follow that path. So I think think that's the only thing you're going to need to know to complete that worksheet. As with always, please evaluate your answer. Does that seem reasonable? Does that seem like, like it should be that large of a number? And if I look at, yeah, I have this huge Avogadro's number here on top, and I don't have very much for, to divide it by, so my number should stay, should be a pretty large number like that. So yeah, that seems reasonable. All right, hopefully that helps. You can watch this video as many times as you need to for clarification. If you're really struggling, please email me and I'll try to check that and get back to you.